Hello friends, welcome to our channel. In this video, we are going to look at problem 1368, today's daily challenge problem. So the title is minimum cost to make at least one valid path in a grid. So this problem actually is a typical problem for practicing Dijkstra's algorithm. So here we are given a m by n grid, and each grid has a number. So 1 means go to the right, and 2 means go to left, 3 go to the lower cell, and 4 go to the upper cell. So we will initially start at the 0, 0 position, and the invalid path in the grid is a path that starts from the 0, 0 cell and ends at the bottom right cell, following the direction on the grid. So the valid path does not have to be the shortest in the sense of count the number of cells it passes, but we can actually interpret shortest in the sense that it uses least amount of modifications of directions. So here you can modify the sign on the cell with cost equals to 1. So you can modify the sign on a cell one time only. So we want to return the minimum cost to make the grid have at least one valid path. So here first we need to notice that it's always possible to get a valid path as long as we do necessary direction change using this operation, right? So here actually we interpret this problem because the problem is minimum cost, right? So this is actually give you a hint for Dijkstra's algorithm. But here the cost is the number of direction modifications in a potential valid path, right? So we want to find such a path which needs a minimum number of modifications of direction. So if you look at the two examples, so here example 2, we need we just follow this yellow, red, green, and follow this brown one, this green one, and red, and then arrive at the destination. So this requires 0. You can also look at the explanation, right? So here you change direction, and here you change direction, and here you change direction. The cost is 3, right? So here actually you just need to, let's see, follow this one, you arrive here, then change direction, you got here, so 1. So this is the problem size. Notice that m and n are both bounded by 100. Therefore, there are at most 10,000 cells, right? So also the grid ij is 1, 2, 3, or 4, right, as given here. So this is a typical Dijkstra's algorithm problem. So let me first recall, right? There are 2 ingredients in Dijkstra's algorithm. First is a heap, right? Of course, if you want to store the distance, you also have some dictionary. That's the data structures are going to come into play. Another one is relaxation, right? Relaxation. So basically, this says that if you arrive at a position and u, this is the cost, right? That's cost u. Then from u and v, there's another cost from u to v. If this is less than cost from the source to v, then actually we replace the cost from the source to v as cost u plus cost uv. So this basically means that the cost from the source to v is can be improved by v of u, because the cost from by v of u then arrive at v is less than this one. So this is the relaxation. So once you realize or pay attention to these 2 parts, typically you should be able to write a correct Dijkstra's algorithm solution to this problem. Let me carry out this program, and in between you can follow my thought process. First, I want to get the number of rows and number of columns. So this is the very standard, right? And also, I want to define a function to get the neighbor of a position. So here I want to define get neighbors. So given a position ij, so I want to get the 4 neighbors possible. So we want the neighbor to be inbound. So I want to do this xy for xy in this one. So I minus 1 j, and I plus 1 j, and I j minus 1, and I j plus 1 for let's see, if not for, if they're inbound, right? This is greater than or equal to 0, less than m strictly, and we also want this y is in this range, greater than or equal to 0 and less than n strictly, right? So once we have this function, so I also want to have a table. So this table is for lookup. So if the grid value is 1, so we're going to move to the right. So I want to write like this, right? This is the direction. And 2, it means 0, negative 1. And 3, so it's go up, right? So 4, 3 is go down, 4 is go up. So we have negative 1, 0. So these 2 are preparations. You can write in this format, or you can choose not to write in this format. That's not essential. So first I want to have a dist. So this is going to store, given a position, what's the shortest distance from source, or shortest cost from the source 0, 0 to that position. So I'm going to use collections default dict. So I'm going to write a lambda, so associate the value to be infinity, right? So because the source is 0, 0, so I will write like this. So you can write like this because this is interpreted as a tuple, or for explicitly you can write like this. This 0, 0 equals 0. To save some typing, I'm going to write in this format. So with that said, we also have a heap, right? So the heap will store current distance and the source. So this is stored what? The distance, the minimal distance or minimum cost, right? Minimum cost. And ig, right? So this min cost means that from the source 0, 0 to the current position, what's the mean cost, right? So then we can actually carry out the Dijkstra's algorithm. So basically it's a while loop, while heap. What should we do? Because the heap, each time you do heap pop, you always get the nearest position to the source, right? Currently with the current element at the heap. So what we get is distance or cost, ig. So it's going to be heap q, heap pop from this heap, right? So here, once we get this, let's first do a quick check. If I equals m minus 1 and j equals n minus 1, this means that we have already arrived at the lower right corner. So we immediately return this d. This is the minimum for sure. So otherwise, what we do? So actually, we can do this. Actually, this is not necessary. Let's first write it here. So we set this to be d. And then what we are going to do, we check the neighbors. So first, let's get the neighbors. Get neighbors ij, right? And then also we need to get direction at the current position ij. So let's call it di dj. It's going to be the table value at the current grid value, right? Grid ij. Then we are going to examine the neighbors for xy in neighbors. So if from the current position ij, so we can directly arrive at xy according to the current direction, right? So there's no cost, right? So let's first check if I plus di equals x and j plus dj equals y. It means that this xy is exactly following the direction at the position ij. So in this case, there's no cost. So then basically we want to check d, the current distance at ij. Then from this arrive at this position xy, no cost. So we want to check if d is less than this xy, right? So if it's less, so we can actually set this position to be d. Then we do heap q, heap push. We push this information into the heap. So the information is this xy and xy, right? So this is one. Otherwise, so if following the direction in the current position ij, we cannot arrive at xy. So in order to arrive at xy, we need to make a direction change. This increments cost by 1. So we are going to check if d plus 1 is less than this xy. So if this is the case, so we're going to set this xy equals d plus 1. And then we push this information into the heap. So it's this xy again, right? Then xy, right? So these two parts here actually is this if and else block is actually for relaxation. So this is the heap part, right? I will say this is the min heap. So this is the two parts we mentioned at the very beginning. So now, because we are always able to arrive at the lower right corner. So actually, this is the code. So because we have already checked here, so you don't need to write anything here, right? So you can do a test. Yeah, it passes all the cases. Now let's look at the generic case. Yeah, it passes all the cases. So here, let me make a quick summary. So from the problem statement, actually, you can see this problem is a shortest cost problem or shortest distance, but you interpret the distance as a cost. Then you formulate as Dijkstra's algorithm practice. And then you pay attention to the two ingredients. One is a heap, min heap. One is a relaxation operation. So once you realize these two, then writing the code is sort of routine. I guess with that said, that's about it for the current video. Thank you for watching, and you are welcome to explore our channel for other practices. Thank you.